So now I will preview of this and show you how to assign different materials. So here you might assign the material according to the site or the city that you're using, the climate zone of the city. For example, if you're having Cairo as the city, you're going to assign to be to what? Here we have a component which is called Honeybee Search EP Construction. And here's the library, a Honeybee call from EB Construction Library, and you hook it up here as an EB Construct list. The standard is which type of standard you want to use. And as I told you, you can hover over each title and check what is written inside. This explains what you want to use. In this example, I have used ASHRAE 189.1, and as it's number 3, as you can see, and the climate zone is 2B. And I will also tell you how to know your climate zone. And here the surface type. The surface type we have is when you hover over the title, you can see that you have 0 for wall, 1 for roof, 2 for floor, and so on. So here we have number 4 because it's the window. And now we can know which type of material we are having for our window. And here, as you can see, this is the type of material. If you want to know more about it, you can bring this called Decompose EP Construction, Honeybee Decompose EP Construction, and you can start bringing panels and hook them up to know the material, the name of the material, and if there are comments, and also the value, the U value. You have to you can hover over all these values to know what exactly do you want to attach in your schedule or something, information about the material you're using. And as you can see here, I took this material and hooked it up here in the window EB construction, and here also in the window in the EP construction in the component of the window to wall ratio. These are the same as the previous one. Here you just change the surface type. For example, it's 0. I'm having a keyword I want to use in a specific material, so I came up with this. And this component is called Honeybee Set EP Zone Construction. You hook it up here from the last component you have for your Honeybee model, which was the solve adjacencies hooked up after the assigning the windows. And you hook it up here and you start select the materials you want to assign. For example, I left here the floor EP construction and the exposed floor. And actually, Honeybee assigns a default materials for anything that is left. And so here, now I will go to the EPW file part, and I will show you how to know your the zone, the climate zone you're in. Here we have Cairo, and I will show you also how to bring the link for your EPW file. This component is called Open EPW and the Stat Weather files. And here you can go to Energy Plus, click on it. You have here weather. Inside weather, you can choose, for example, let's say we want London. So you have United Kingdom. And here you can choose between different cities. And so here I will check on for London. I will right click on download all and copy link address, and then go here and clear this and paste this link. Then click outside the panel. So it's okay, it's working. This is how you assign a specific city to bring its EPW file to perform the simulation to know which honeybee, which climate zone are you in, and also to perform the daylighting and so on. So here, this component is called import stat. You from this component, you take the stat file and hook it up here, and you can find the ASHRAE climate zone for the city is 4A. Now I'm going to take this ASHRAE climate zone and hook it up in the climate zone here instead of the 2B, which was for Cairo. So here, climate zone and climate zone also. Now we don't need this anymore. I'll delete it and go back here. So now we have created the energy model. We want to perform the simulation. So let's move to the energy simulation part. I will actually turn a preview on the last one. And here we have a problem concerning the honeybee windows. So we need to know what is it. The number of items in the EB construction list does not match the number in. So the problem here is that the number of materials does not match because we have two materials options. So we needed to choose one from them. So I will here make list item and hook up this list. Choose, for example, 0 as the item and hook up this here. Now the problem is solved. So here comes the energy simulation part. We bring this, which is called run energy simulation. It has different titles. So here for the north, if you wish to change the default north, you can do it from here. And the default north is with the y-axis. And here the EPW file that we have brought before is hooked up. So I will bring it close to this so that you can see it clearly. It's the EPW file, which is hooked up here in the EPW file part. Analysis period means that if you want to choose a specific period, if it's not an annual simulation. So here you might choose to simulate your building for just one day or for a month or so on. So let's change it from the default, which is annual, because we need to not increase the calculation time to simplify the thing as much as possible. So we have here the analysis period, and you can see that start month, let's say that it's 1, for example. The start day is 1. The start hour, maybe 1 also. It doesn't matter for me. It's just I want just to show you an example. So I want to minimize the calculation time as much as possible. So the end month might be 1, and the end day I might take 2 because I want to make just this period. The end hour might be also 1 for the next day or 2 for the next day. The time step, you can choose which time step do you want. So it's you might want to make it an hourly. So here I might choose to have it here we have the honeybee zones that we brought from this component, the last one. And here we have the simulation outputs. Here you can choose which outputs do you want to bring. And in this case, I just want the zone energy use. And then finally, you have to turn the right IDF to true and the run energy plus into true also. And then we have here a component which is called read EP result that we need after performing the simulation so that we could take the results of the total thermal load. And before performing the simulation, I will show you first how to add the shading devices. And here we have this, which is called Ladybug Shading Designer. You need to hook up the glazed surface, which is the windows only, that we can bring from the honeybee decompose based on type. And I will bring from here the windows, hook it up here in the glazing surface. I can turn this preview on so that you can see the shadings coming out from the windows. Here, you can assign the depth or vector for each of the shading devices. Number of shades, determine the number of shades for each glazed surface. And in order to minimize that calculation time, I will choose to have just one shading device for each window, of course. As you can see here, it's just one shading device. And the distance between, no, I don't have distance because, but actually this, the distance is not important for me. Run it means that we're going to run this component horizontal or vertical. You need to choose whether you want your shading devices horizontal or vertical, and you can make both, of course. So it's set true if you want to generate horizontal shading devices. And in this case, I'm generating the horizontal shading devices. Here are the shading angle and the north and so on. So this is very important because here you determine the shading devices for each, the depth of the shading devices for each of the facades. And as you can hover over here, you can see that it starts with, it has four values. It starts with the west, the south, and east, and so on. So you have to hook up four in the same order. So here I will assume that I have a depth which is starts from 1 to 2, for example. You might assign 0 if you want. So maybe 0 and 1, and that's enough. So we have the option for 0 or 1. And we might use this in just one facade so that we can minimize the calculation time, as I've told you. So here, the 0, item 0, we start by the north, west, south, and east. So let's assume we want to choose to manipulate the south facade. So I will make the 0. I will remove all these numbers, and here start by, also disconnect this, and then I will start by making zeros for the north, east, and west, and I will have also only the south that's going to be manipulated. So here I hooked up this first, and then shift and hook up the second, the third, and the fourth. So now we have a third dynamic parameters, which is the horizontal shading devices that are created in the west, as you can see here. So Now you will, in order to hook up the or to make the simulation count for or consider the shading devices, you need to bring what is called Honeybee Energy Plus context surfaces, and hook up the shading surface into the shading surface, and then bring the Honeybee context into uh, the Honeybee context here. So now the simulation counts for the shading devices. And now you can start. Before start running your simulation, there's something that I want you to do. If you find any problems in the simulation, anything that's not working well, and you don't know the solution for it, that here you have solution recompute. This makes like refreshing your canvas. So if there is a problem with sometimes errors occur without a reason. So just by making recompute, things change. So if you're having a problem with running the simulation, before trying to solve it, first check that you're having that you made the solution recompute, and then start, if the problem remains, start searching for the specific reason behind this problem. So here I have false, and then I will double click to run the simulation, and this means that the simulation is running. So we will wait to see that the Energy Plus component finishes the simulation without any problems, which means it doesn't turn into orange, for example, it doesn't turn into red, and so on. This is a problem with the memory of my computer, and it's nothing. Do not take it into consideration. So here I will wait until the calculation time finishes. So as you can see here, the simulation was performed in a good way. I don't have problems with my simulation. And here, because we have decided in this component which output do I want, so here there is specific outputs coming out from the result file address. So here we can have the total thermal load. We can choose to manipulate the cooling load and the heating load separately, but here it's taking the total thermal load, which means both the cooling load and the heating load. And here is a visualization for the simulation that you will find in Ladybug and Honeybee. These are scripts, already scripts that you can take and use. So here you need to hook up the zone data, which is the thermal load, total thermal load here, and the Honeybee zones from the last component that has the materials. You can take it and hook it up here in the Honeybee zones. So now I will. So here, in order to see the zones colored, you need to make sure that the low bound and the high bound matches with the results coming out from your simulation. So if I started to look here, for example, in the plan, I can see that I have the low bound is 800 and the highest bound is 6400. So it's fine. We don't have a problem with this issue. So here I will choose. I will start removing this. This preview on here. I will turn it to preview off. So now you can see the zones, the floor is colored with the results of the map. And here you can preview on so that you have the whole zone colored with the energy use. So here, This is in terms of visualizing your model. So now we want, for example, if we want to bring uh, the energy use intensity, which is the total or annual energy consumed by a building per unit area. You can bring this first. You can separate data so that you could have the numbers alone and the strings alone. And here I brought the numbers, and I'm going to bring a component which is called honeybee normalized data by floor area. You hook up the results in the simulation data and the honeybee zones from the materials, the last one, which is the materials. You hook it up here, and then you can find you can have the normalized data for the energy use intensity, which is reflect the energy use annual energy used per unit area. So here now we can go to we can use this as they can show this panel. Here you have the total number of energy used. You can bring a number and rename this number thermal load, maybe total thermal load. And then you have one of the objectives. Now we will go to Octopus. And here is the objectives. So I will hook. You can start by press shift if you want to use more than one objective. So here we have the objectives, and now we have the values for different dynamic parameters. As we stated here, for dynamic parameter, I'm going to hook up by using shift to hook up more than one value for the dynamic parameters. And we have also the windows, as we have stated, are going to be used as dynamic parameters. We have also the shading devices for the north, for the south elevation, which is going to be manipulated during the experiment. And now I will remove this old Octopus component so as not to be confused. And now here, before starting the optimization, I want to show you how to use the TT toolbox. The TT toolbox is used to record the dynamic parameters, the values of the dynamic parameters with their corresponding value of the objective functions during the experiment. It's very important to use it because Octopus doesn't show the number of the values of the dynamic parameters. It does only show the values of the objective functions, but you will not be able to bring the values of the dynamic parameters from Octopus after finishing the optimization. And here we don't have a lot of dynamic parameters, so I don't need all these components. It's a component which is called Colibri parameters. You can find it in the TT toolbox, and you can download the TT toolbox from Rhino or Grasshopper. There's their websites. So here, in the previous experiment, because I had a much complicated model and a lot of values for the dynamic parameters, I needed more than one component because TT toolbox causes errors with a component that has many values. So I had to divide them up into different lists. So here, let's take these values of dynamic parameters. We may also change, you may bring a new one, which is Colibri parameters. parameters, and we can remove this. We have here only 3 values. And we have here, and also the number of, sorry, the name of the slider counts in the idea of making errors if we have too many data. So it's better that I simplify the name of, for example, X. This is going to be better to have X instead of have data 3. It's better to have sliders with simplified names. So here I might say S for shading devices and hook it up here. And I might also change these to maybe F1, which is the form, F2, and F3. And hook them up again so that I could simplify the names and have minimize the number of letters and values in general in this Colibri component. And now I will hook up the result of which is the total thermal load. So we have here the parameters. I will go up here to this component which is called Colibri aggregator. I will remove these components because I no longer need them. I will add this to the group and we'll choose here to put this as the genome, and here it needs a phenom parameter. So I will remove the thermal load and take this again and go here to take parameters. I will take the total value. We need the total value, not the energy use intensity. So I will take this total value, remove this one. So we have here, again, I need this one instead, but no problem. It's going to be the same value actually. It's not necessary to take this one. So it's R is enough. I'm going to remove data 2 and go back here and hook up the phenom so as not to get any errors. Now add to group, and here you choose the value, the folder where you want to put, let's say that YouTube, for example. Okay, now you can see that in the C folder, here in the C, you will find something that is called YouTube. Once you hit true, so here you will find in the C the YouTube file, which will contain an Excel sheet with the extension .csv that will contain your data. So if you click on this sheet, you will find that you have the F1 as we have stated before, F1, F2, F3. You can then know the different values by knowing that they have different names. XS and the out is R. Image is the image in the Rhino that is going to be also saved during the experiment for each dynamic parameter, but you don't have, you will not be able to use it because you need to work on providing a good rendering in these images generated or saved by the TT toolbox. So now I will save my files. You need to do it actually from time to time, because sometimes you might lose the electricity or something that you don't, and then you will not find your data available. So here in Octopus, I want also to mention that Octopus is better than using the other optimizer that was an old one, just called, I don't remember its name now, because Octopus does save your data. So if you're going to perform the optimization and then close the Grasshopper and Rhino and then open it again, you will find your data still available inside the component by right-click here. I will reset because it doesn't have anything. But here we have just one component, one objective function, and we want to use what is called single objective optimization, while in this case, in order to be able to do single objective optimization in Octopus, you will need to assign a diversity parameter as a second objective, because it doesn't run single objective optimization on its own. So here we have chosen to add the diversity parameters. So you will find here total thermal load, which we have hooked up before in the objectives. And here you can control what you want to do here. You can control some parameters inside Octopus. The maximum generation, for example, let's assume we don't want to have more than two generations, where you can control this here. Here we have different, I will show you this after performing the optimization. So I will start. It's going to take some time, so I will leave you and come back again after finishing a considerable number of configuration of simulated configurations.